Welcome back to our fourth video for pre-AP chemistry, and we're discussing models of the atom. Now, in the last unit, what we discussed was the Bohr model, and we want to look at how Schrodinger differs from the Bohr model. But before we do, let's take a quick review of what was good about the Bohr model. Remember, the Bohr model discussed that we had energy levels, that those levels were quantized, meaning only discrete values of energy were allowed. It helped us understand atomic, and we saw this in class, emission, spectra, and that's where an element goes from a ground state into an excited state, and then from an excited state, and remember that was from low N to high N, and that involved the absorption of some sort of energy, a variety of energy, and we called that excitation. And then we talked about what happens once it's in the excited state, that it doesn't stay there for long. It goes from that high N back to that low N. And in the process, it's going to emit electromagnetic radiation. And that's why we call it an atomic emission spectrum for each element. Now, let's take a look at Schrodinger's equation and how the Schrodinger model helped us, or Bohr's model helped us, but then it led us a little bit astray as well. Now, Schrodinger agrees with Bohr about those quantized energy level. So that was awesome. That was a huge boost to our understanding of the element. Now, Schrodinger differs in one key aspect on the Bohr model. The Bohr model ultimately talked about electrons moving in an exact pathway called an orbit. And we still have teachers having students do that, what's called the planetary model of an atom. And honestly, it drives me crazy, because then students have this misconception, you know, people sometimes for decades, that electrons orbit a nucleus. We don't really know how electrons move. That's why I like to call them the elusive little electron. What we can do is come up with a math equation that describes a space with a high probability. And even then, we don't know the exact motion. We're talking about probability of finding an electron with a given energy. And in fact, that's what we will define is an orbital. I'm sorry, if I was queen of the world, we would not have called this an orbital. We would have come up with something a little bit different, because an orbital does not mean electrons are orbiting. That's not right. All an orbital is it's a region in space where there's a 90% probability of finding an electron with a given energy. At our level, I like to call these the electron playground. And that's what we want to do, is build up models to explain where the electrons are in an electron playground area where we have a 90% probability of finding an electron with a given energy. Now, there's so many analogies about that. There's analogies about the classroom. If it's actually an A or a B day, but if it's first period between 8:15 and 9:15, I have a 90% probability on a Monday through Friday that you're going to be in my room. But we don't know where you're going to be in my room. The desks get moved. We may be doing a lab, and you may not even be in my room. You may be absent, or you may have gone to the bathroom. But we can still describe my classroom as a region in space where there's a 90% probability of finding a student during a given class period. And that's what Schrodinger's model did for us. And it's called a quantum, because energy is quantized, mechanical model. Now, his model involves some pretty heavy calculus. And Schrodinger's model can be solved fairly readily for hydrogen, but we need much more complicated models that scientists use for substances above hydrogen, or with more than 2 electrons, say. But this gives us a great model for laying out where electrons are, and hence we can understand electron and atomic structure. And if we understand the structure, we can understand the function, and that will in turn help us understand bonding and develop medicines and all sorts of wonderful things in life. So we're going to first talk about the electron location. If I want to define the location of anything in space, I need 3, right? I need to define 3 coordinates. Now, in a room, we're typically going to define an X and a Y and a Z. But with an electron, I don't have this defined space. I have a nucleus. And so I have to define my coordinates around or with that nucleus as my reference point. So I need 3 coordinates. It doesn't do me any good to come up with X, Y, Z spatial coordinates, because then what if the nucleus moves? Then those X, Y, Z spatial coordinates are not helpful anymore. So we needed a coordinate system, and that's what Schrodinger's equation gave us. And that coordinate system, the symbols that came out of that calculus are N, L, and M sub L. Now, we did get a bonus one called S. So there's a bonus coordinate called S or M sub S. So we really have N, L, M sub L, and technically that's called M sub S. We simplified just a little bit for you guys here, but I prefer that notation. So let's take a look at the first one, and the first one's going to have overlap with Bohr's number. N, which you saw in that diagram before, is called an energy level. So we're going to have symbols and numbers for most of these. That's why it's called a quantum number. At the pre-AP level, we're primarily going to focus on the symbols, kind of the furthest from the actual mathematics that we get. Once you get into AP, we focus a lot more on the numbers that are involved in this. Now, this energy level, what's key about this energy level is it provides 2 key indicators. It provides an indicator of distance and energy. Now, I want to tell you something a little bit here about this. The distance is going to stay true for our value of n. In other words, the higher the value of n, the further away the electron. Now, as we try to model larger atoms with Schrodinger's equation, which is really for smaller atoms, we do see that the distance stays true, but unfortunately we are going to find that the energy, our energy, gets a little mixed up. It's not going to go quite in the order that we think it will. But that's kind of the bad news. The good news is the periodic table is going to tell us everything we need to know. Okay, so in general, the higher the value of n, definitely the further away. And in general, the higher the energy level is. Now, the number of electrons in any given energy level is given by 2n squared. And an energy level doesn't start at 0. Remember, it starts at 1, not at 0. And it's given by 2n squared. And so we find that if n is equal to 1, we can only have 1 squared times 2. We only get 2 electrons. Well, if you think of a sphere, the area of a sphere with this small radius can't hold very much. But as that we get further away, the sphere gets bigger and it can accommodate more electrons. So if n is equal to 3, 3 squared is 9, that would give us 18 electrons. So the further away the electrons are, the energy level is, the more electrons it can fill. Now remember, all of this is about balancing electrons' attraction to the nucleus, particularly the protons in the nucleus. That looks kind of like neutrons, so let me spell that out. Nucleus, and particularly the protons in the nucleus, and electron-electron repulsion. So they want to get as close as they can, but they don't want to get too close to one another. And at this point, yes, they're close to the nucleus, but they're getting a little too close to one another for comfort, and so not as many fit. So there's 2 examples here. How many would be in the second? So we'd have 2 times 2 squared, so that would give us 8 electrons. 2 squared is 4 times 2 is 8. And if it was the 5th energy level, we'd have 2 times 5 squared. That's 25. Wow, we can hold up to 50 electrons. Okay, and that's what we'll be looking for. And you really want to remember that formula, 2n squared, for the number of electrons in an energy level. All right, we're going to move on to the other quantum numbers, but until then, this is signing off.